Hi, everyone. Thank you, Max, for the introduction. I'm really excited to be here. This is actually the first time that I've represented Amel Energy in a European forum. So very, very excited, and thank you and for the warm welcome. As Max mentioned, I'm the CEO. I'm also the founder of Amel Energy, and we're all familiar with lithium-ion batteries. We might not all fully understand that they were made with toxic solvents and PFAS-related binders. So I founded Amel Energy in order to solve that problem in the simplest way possible. So the solvent is toxic. It's called NMP. A lot of us might know that already. It's used at scale, and the binders are synthesized with PFAS typically. So this is a PVDF-based binder. And regulatory commissions are increasing restrictions. So even over here in the States, the EPA still remains firm. Their determination on the toxic solvent is that it represents a quote, unreasonable risk to human health. And my understanding is that the ECHA is also very strict on NMP use. And for PFAS related materials, Europe seems to be pressing forward with banning or potentially banning materials that utilize PFAS. If there's an alternative available, we'll be looking at companies being pushed toward adopting that alternative on a time frame. And these materials are expensive. They're not likely to decrease in cost. And typically, this is a US focus, so they're not domestically sourced, and most of it's made in China. So our approach is that we are using a non-toxic solvent that's bio-based. It's generated from corn feedstock and biofermented. It's made in the United States. And that non-toxic solvent is actually paired with binders that are PFAS-free. And this avoids regulatory issues, fast-track permitting processes for new plants, and they're also reducing cost. So our solvent approach is 2 times cheaper, and the binder can be up to 10 times cheaper. So those instant savings could be realized by customers through a domestic supply chain. This is especially important for the United States right now, but we're very open in seeking that partnership with Europe. There's no issue in terms of exporting materials, and we're also looking into the option of setting up manufacturing sites in Europe to service customers. So to speak a little bit more toward the materials, the company itself is a materials company. We're not a battery company, and we're not focused on manufacturing batteries. We actually want to sell the solvent binder as a package to our customer, which is a lithium-ion manufacturer. And right now we're looking at a second generation approach where we pre-combine our polymer and our solvent together to sell to the customer. We have future generations and novel chemistries we're working on. So this is designed to also be a true drop-in replacement for the cathode. And this doesn't require any equipment changes, so no CapEx is required to adopt our materials, and it's compatible with everything that can be put into the cathode. No coating on the cathode is needed, and any conductive carbon, CNT, carbon black can be used. We have 2 pending patents that are protecting this approach, and that's wholly owned by the company. We actually brought this to pilot scale. So we're coding here in the United States in Massachusetts. Flagship university is University of Massachusetts. We have access to a roll-to-roll coder. So we've scaled to 1 liter, and we're able to show with industry standard equipment moving to technology readiness level of 5. And we further were able to build pouch cells. These are 80 centimeter by 100 or so. They're totally NMP free, PFAS free, made with NMC 811 paired with a graphite anode. And we had no major construction issues. We've hit our targets for the year, and we're supported by grants entirely. So Massachusetts is a clean energy center, and in New York State, they have the energy storage engine, which is funded by the National Science Foundation. We have our first signed letter of intent to supply Custom Electronics Inc. as our first customer, and that's a granted pilot that's funded. So we proved within about 6 months, going from coin cell performance parity against PVDF to pouch cell testing, that we're able to scale. And now we're looking at this pilot where we're working with the customer to introduce our materials into 18650 cylindricals. And what we're looking at is building out our R&D center, increasing our hiring, but we also want to accelerate the business development. This is where Europe is really important to us because we want to be able to move from our established beachhead of DoD contractors in the States to be able to service European customers. And we think we're really well positioned to do that. We're supported by what we call the battery capital of the United States, and that's in upstate New York. Now, I wanted to pull attention to why this is important for Europe because we're targeting entering European markets and working with customers between 2027 and 2028. Right now, we're focused primarily on the United States and looking at early adopters, but we're very open to working with any pilot applications within Europe. And the reason why is because the European market for solvent binder is going to drastically expand our ability to obtain revenue. So as I mentioned, our customers are lithium-ion manufacturers, and basically we're looking for anyone within Europe that is interested in moving away from PFAS and NMP. And we can show as a business model, 1 gigafactory, if it's a typical size, we can save 53% cost on materials, which would generate significant revenue for Amel Energy. And further, we actually reduce greenhouse gas emissions by up to 70%, which is really important, especially for reaching carbon negative and carbon neutral goals. And our team, we know, is primed for success. I'm the CEO and founder, as I mentioned, but I have 10 years of experience working at A123 Systems. And our CXO, Sid Paneer, he actually is started and sold his first clean tech startup before joining Amel Energy. With that, I want to thank you, open up the floor to any questions, and we'd be really happy to meet with you.
All right, thank you, Derrick, for your question. There are already 2 questions in the chat, but maybe let me start with a hopefully very quick one. From my time in the research lab, I have to say PFAS materials in general are amazing regarding their properties. Yes, they are harmful, that is a big disadvantage, but my question is, how do you rate the quality or the performance of your solutions compared to PFAS, just focusing on the properties?
Right. So one thing that we are doing and we have succeeded in at the bench scale is fundamental studies of our binder and our solvent, how it affects mixing and coating operations. We use rotational rheometers to be able to measure viscosity and changes to flow patterns. We're using industry relevant slot die equipment, 6 inches wide, so we know that it's coating well onto the foil and we have no drying issues. So we're looking at, as a materials focus, making sure that a manufacturer could rapidly adopt the material. On the flip side, we're looking at the cell results. We just had the pouch cells built and tested, so we're looking at that data right now. But we do have parity in terms of PVDF, so we're able to get the same energy density, the same efficiencies, and we're looking at the cycling performance right now.
Then the first question we have in the chat from Christoph Ziara, he wants to know, do your solvents also target electrolytes?
Not right now. Our focus is solely on the binder and the carrier solvent for processing slurry.
All right, and then just a follow-up question from Christoph, is your technology based on CCU?
No.
Maybe, Christoph, you can elaborate what you mean with CCU for the audience.
Hi, everybody. So it's using carbon CO2 as a feedstock with a catalyst to produce actually the material that you're looking for. So in this case, solvents, for example, cyclic solvents, or as a feedstock for electrolytes, which could be a precursor also for solvents like MEOX, which can also replace NMPs. I agree with Derrick that the replacement of NMP is a key, and it's very important for building up a consistent battery manufacturing at scale.
Thank you, Christoph. Yeah, so our feedstock is actually, so we get the solvent from a supplier, and the way that they manufacture it is from corn, and they do a bio fermentation with bacteria. It's a very efficient, low energy process, and then they just filter it. So
Okay,
it's a renewable source.
perfect. I'll be back to you. I have a very nice sauce for you for that.
Great, thank you.
Perfect. That's what this
I saw
form is
another
about.
question in the chat about sodium technologies. I wanted to clarify, yeah, our approach, the reason why we chose to go a non-aqueous route is that we wanted the flexibility to stay as an organic solvent package and be able to service any type of cathode, whether it be sulfur, sodium, anything exotic we're willing to look into. And we believe that, this might be an easier way to go than going with some aqueous solutions that need pH balancing, that can experience gelation problems. And I understand that sodium can have that issue. So
If you allow, I have one final question, a short one. Does your solvent always come with a binder as a system? So you always have to regard the binder with it in the application, or can you also use standard binders in this regard?
that's a great question. So what we've done is we've screened several different compatible binders. So one of the catches is because of our solvent change, we're not able to use PVDF. So a customer would need to change to a different type of binder.
Yeah.
But we've identified several chemistries and families of polymers that are soluble. Our future looking approach is actually emulsion-based polymers. And in that case, you can use basically any chemistry that you would like. That would be a nanoparticle suspension. So now we're looking at point-to-point binding within the electrode microstructure. We believe that could actually, go ahead.
Sorry.
I was just going to say that could potentially even boost performance due to improvements to ionic conductivity.
Okay. Completely clear. Thank you. Thank you, Derrick.